to look at the addition formulae for sine, cosine, and tangent, as well as the double angle formulas for sine, cosine, and tangent. So this is just a review from class up to the point where we didn't quite prove why this worked. So I'm going to start giving you the rules or the identities that we're going to show. So jot these down in your notes, and you need to know these, okay? So the idea here is that, you have two variables, okay, A and B in both of these. And the examples that we're going to do are just going to show you the idea of how these work rather than, well, we're going to show why it's useful, but they're most useful when you know what sine of A plus B is, and then you either don't know A or B and you're trying to solve. So this is kind of another one of those tools that you can use to solve problems. So make sure you have these down in your notes, and we're going to go and look at why these are so. Okay, so the first thing is we got into class, we got to the point of why this works, right? So we have two variables that we're trying to solve for, and we need two equations, basically, if we're going to try to isolate either one of those or have our equation in terms of both of those without having any additional factors in there. So basically, if we're trying to find, okay, so basically we have segment PQ, right? And you'll notice that's this one right here, that's blue. Okay, and we have angle A, which basically we're pointing all the way to the x-axis, and angle B is going all the way from here to the x-axis. So you'll notice that triangle PKQ in our unit circle is a non-right triangle, which means that, if we're trying to find the value of the angles, we can't use Pythagorean theorem straight out because it's not a right triangle. That's why we are going to be implementing the law of cosines, or as they say in England, the cosine rule. Okay, if you didn't go over this when you were in geometry or algebra 1, it's probably a good idea to review it, but I've written it here and I'll explain it, but you may need a little more practice. So the basic idea with the law of cosines is if you don't have a right triangle, you can't use SOHCAHTOA, right? So you would use the law of cosines. But you can only use the law of cosines when you either know two sides and the angle opposite of the side that you're trying to find, or you know some other combination of the two factors that you need for this formula. Like you could know all three sides but not know the angle. So you need to have some knowledge of at least three components of this formula. Okay, so basically we can write the area of this triangle, or not the area of the triangle. We can find PQ in a whole bunch of different ways, right? We could use the distance formula, but then we're going to have PQ squared equals something, and that's not just in terms of sine or cosine. So let's go ahead and try to get this as simplified as possible based on what we did in class. So the first thing we did in class was we wrote the distance formula, right? We said PQ squared, that's that segment up here, PQ squared was equal to, the distance formula is the cosine of B, minus the cosine of A. This is just a straightforward distance formula that comes after Pythagorean theorem. And then in class we simplified this even more to look something like this. Okay, so here I just expanded out both binomials by squaring them. Okay, and this is what I did. I did a whole lot of terms that look pretty complex, but this actually simplifies down pretty simply, so let's look at that. Okay, so basically we know that the sine squared of theta plus the cosine squared of theta equals 1. So basically we need to find sine squared of b and cosine squared of b, and if they're added together they equal 1. So here we have cosine squared of b plus sine squared of b. Well, that equals 1. So those two together make 1. So we say PQ squared equals 1. basically, this whole thing, forget the picture. We've got too many, but anyway. Well, we still have PQ squared here, and the goal is not to have PQ squared. We want to find the angle because these are addition formulas for angles. So the next step is we just want to have this formula written with cosine and sine, right? Inside and nothing else. So if we look back up at our unit circle, let me ask the board and go to the top of this particular board for each. Okay, so basically we need to find PQ, right? So we would call PQ side C here, okay? Because the angle that we have is opposite. So what we would say is this side C is equal, like its opposite angle would be this whole thing is A. This partial angle here is B. This little teeny line, okay, right here. Oops, I scrolled down it really. This one right here would be A minus B. So we could call this angle right here A minus B. All right. Okay, so that's A minus B. So in a unit circle, if you'll remember, all the radii have a distance of 1. So that means A, either one of these, it doesn't really matter. A is 1 and B is 1. So really, all we have to plug in here is C, the cosine of big C, not little c, because little c is the side. So A, B, little a, little b, little c are all the sides. The capital letter C is the angle. So equals A squared plus B squared minus 2 times A times B times the cosine of angle C, because that is A minus B. Okay? So if we simplify this down, we end up with PQ squared equals 2 minus 2 cosine A minus B. Okay. Substitution. So I'm going to say, really, the pen, I'm going to say it, 2 minus 2 times the cosine of A minus B is equal to 2 minus 2 cosine B times cosine A minus 2 minus 2 sine A. All right. So basically, we're going to do this little messy math here. I've got a positive 2 here and a positive 2 here. That means that I need to agree to add them to both sides, okay? I also have a negative 2 here that I'm going to divide off of both sides. So I'm trying to get the angle by itself because we use angle addition property. So now I have cosine of A minus B. When I divide the negatives off, I get 1 times this. And just for order's sake, because we like to be orderly, I'm going to always write my multiplication with A then B. So cosine of B times cosine of A, just as a reminder, is the same thing as cosine of A times cosine of B. So I'm just switching them around by changing the value. And then negative 2 divided by 2 is positive 1. And it ends up being 1 times okay? So these two equal each other. This makes this an identity, okay? Because they're identical in value. Look what we have. We've just proven that cosine of quantity A minus B is equal to cosine of A times cosine of B plus sine of A times sine of B. Now, if you were to switch things out, okay, with with the other three identities, you could prove them in a similar way. Okay? So you might be thinking, if you're Allison, right, when will I be using these? So here's the deal. Your calculators are awesome, right? They spit out exact values. So really, um, you would want to use these when you were trying to find, if you had a variable that you were trying to find um, that wasn't known, but here's kind of the general way we would do it. So cosine of 15, they want us to find the exact value, which your calculator will give you. But here's how you would use the addition formulae. Okay. So basically, on our unit circle, we have exact values for 30, 45, 60, 90, and so on, but not for 15. It's not listed on our unit circle, but that doesn't mean that there isn't an exact value for cosine of 15. What it means is that we need to combine two of our other angles to make the exact value. Okay, so in this case, cosine of 15 could be equal to the cosine of 45 minus 30. Would you agree that that is equal to the cosine of 15? Okay, I think so. So basically, if we have the cosine of 45 minus 30, in this case, A is 45, B is 30, and this order does matter. It doesn't matter what A and B are when we have addition, okay? But subtraction, it matters a lot, okay? So if you'll remember, if we go back to our formula, we have this, the cosine of A times cosine of B plus sine of A times sine of B, okay? And we can find the answer. So we would say the cosine of 45 times the cosine of 30 plus the sine of 45 times the sine of 30, okay? That gives us root 2 over 2, okay? Times root 2 over 2 plus root 2 over 2. That's not 45, right? Yeah, it's the same. Times 1/2. Okay? So what we end up getting here is root 6 over 4 plus root 2 over 4. And if we simplify it in half, we could write it as a single fraction because our denominator is the same. This would be our exact value. Okay? All right. So this is how it works. But again, it's most useful if, let's say, you don't know A, but you know that the cosine of A minus B is equal to root 6 plus root 2, both divided by 4. And then you can find A if you're given B. All right, so I want you to do example B in your notes, and I'll be checking for that tomorrow. And let's move on to tangent. Okay, so tangent, basically tangent has a little different identity, but you could prove it the same way we proved the other two, or the other one, except that tangent's denominator can never equal 0 because it's undefined at that point. So basically, if you find the exact value of tangent of 75, we're going to do the same thing that we did before. We would say the tangent of, we could say 45 plus 30, okay, or 30 plus 45, or yeah, it's probably the easiest one. Okay, so basically you just plug this in, right? Would be the tan of 45 plus the tan of 30 over 1 minus the tangent of 45 times the tan of 30. Okay, you'll get an exact value if you plug these into your calculator and get them out. But again, the power is if you don't know A or B.